Hello, I'm Douglas Santos and I'll be presenting the paper Analysis of Implementations of Edge Detection Operators in FPGA. So, the evolution of computing systems made possible the development of new applications. Among the emerging applications, we can highlight those using computer vision systems, such as unmanned underwater vehicles, 3D environment mapping, stereo image processing, and autonomous electric vehicles. These applications have requirements and must have solutions that fulfill these energy and performance requirements. So FPGA is a technology that has been employed for these computer vision systems, and it takes advantage of fixed point arithmetic and approximate computing to improve the fulfillment of these requirements. So the edge detection operation is an elementary operation in low-level image processing, and therefore the search for efficient implementations of this operation is crucial. So there are several hardware-based implementations of edge detection filters in the literature, but only a few works evaluated the energy cost and none performed analysis of different filters regarding energy consumption. So in this work we evaluated 6 edge detection algorithm implementations in FPGA and collected all the metrics that are common to embedded systems to have a more detailed analysis of each implementation. So we used as a baseline Python with Float32. With this we used Lena to establish the required fixed point precision to have a CWSSIM precision of at least 80%. We've implemented with VHDL each operator using fixed point and the most common kernel size. For the most of the operators it was 3 by 3, but for one of them it's just 2 by 2. We used to test the BSDS 500 dataset, and for the simulations we used Model C Altera Starter Edition. The metric for evaluation of quality of the processing was CWSSIM, and for the evaluations of performance requirements and silicon costs we used Intel Quartus Prime with Cyclones 5 SoC. For the hardware design we used a sliding window block that is able to gather all the windows of the image to perform the edge detection operation in each of them. Okay, so this is the start of the implementation of the Kenny edge detection operator, which has 2 convolutions with Sobel and a magnitude gradient to gather the result of the lemma. This Sobel is applied as well for Kenny, but we got the theta as well as a result, and we have a lot of steps to implement the Kenny filter architecture that is a bit different of Sobel 1. So in this table I present the similarity among the software and hardware based implementations for the processing of Lena image. We can see that the worst case is Kenny because it is the most complex operations, therefore has the most wrong results. So in this table we present the silicon cost comparison with the implementations of other algorithms. So the Kenny one, you can see that uses the most amount of resources in the FPGA. So we can see that it has a lot more costs. So in this table we present the performance metrics in comparison with other implementations. We can see that Kenny takes a double of cycles to perform its operation, and the maximum frequency of the Kenny is the worst one, reaching 107 MHz, while the Sobel has only 104 MHz, and the best one is Roberts that has a 2 by 2 kernel that reaches 181 MHz. So we can see that the throughput of the algorithms is very affected. So in the table 4 I present the power and energy metrics. So we can see that Kenny consumes a lot more dynamic power between the other ones, while the static power between each of them is not that different, at least so far through Kenny. And the total power of Kenny is actually much bigger than the other ones because of that. And as energy per pixel, we can see that Kenny has 5 times more energy consumption per pixel than the other ones. This is due to the greater complexity of the Kenny edge detection algorithm. Now comparing the result of the implementations in hardware in the BSDS 500 dataset, we can see that Kenny implementation dropped a lot more to 0.75, 0.76 in the precision comparing the software and hardware based implementations, while the other keeps its result as in a constant level. So in this work we performed an evaluation of performance, silicon cost, and quality of edge detection implementations. We know that Kenny presents the best output image, but it has much higher costs. These operators could be applied in dynamically reconfigurable systems, since it could change the algorithm that is configured in the FPGA. So as a future work, we intend to use Otsu method to improve quality of the Kenny algorithm and integrate filters in computer vision systems to evaluate its performance in a real application. So thank you for your attention. Please visit our profile on Instagram, leds.lab, and I'm available for questions now. Thank you.